Resolution of forces number 9. We have a 2 kilogram object which a student pushes up a slope at an angle of 60 degrees. There's a frictional force of 1.0 newtons. Fr equals 1.0 newtons. That will be pointing down the slope. And we're asked, why does the trolley continue to move up the slope even though the force is no longer being applied by the student? That's because they're trying to see if you believe in Aristotelian physics, which means you're about 2,000 years out of date. What Aristotle thought was that for there to be motion, there had to be a force making the motion happen. What we now know is that forces cause accelerations, not motions. Things can move without there being an unbalanced force. So, for A part 1, we're looking for a set of words, something along the lines of the trolley is decelerating up the slope. So the trolley is moving up the slope, but it's getting slower as it moves up the slope. If Aristotle had been correct, then with no force being applied by the student once they've pushed the trolley and their hand or whatever they've used to push it is no longer in contact, the only force would be the friction down the slope. And so according to Aristotle, it should instantly start moving down the slope, which it doesn't do. It continues moving up the slope as it decelerates from whatever velocity it had at the point it left the student's hand, eventually to 0, and then it starts to go back down the slope. So, A part 2. We are working out the unbalanced force. And that's going to be the component of the weight parallel to the slope plus the friction force. So that's going to be mg sine theta plus the force of friction, which is going to be 2.0 times 9.8 times sine 60 plus 1.0, and that should give you 18.0 newtons, allowing for rounding to the correct number of significant figures. Okay, and then we're asked for the acceleration. Now, a bit of a trap there because it's actually a deceleration. So A equals F1 over the mass equals 18 newtons over a mass of 2 kilograms, which equals 9 meters per second squared. So the deceleration is 9 meters per second squared. Or if we preferred, we could say the acceleration is negative 9 meters per second squared. It's the same thing. Personally, I prefer decelerations, but either is correct. So B part 1, the trolley is now rolling back down the slope. And we need to calculate the unbalanced force again if we're going to find the acceleration down the slope. And someone, somewhere, is going to leap into the trap and say that it is the component of the weight parallel to the force plus the frictional force again, except no, it's not. Because the frictional force is always opposed to the direction of the motion. So up here in part A, the trolley is moving up, so the frictional force is pointing down the way, but down here in part B, the trolley has stopped and is now rolling down the slope, which means that the frictional force is now pointed up the slope rather, so we are taking it away. So here, mg sine theta pointed down the slope, here mg sine theta pointed down the slope. Here, friction and the component of the weight are in the same direction, so we add them. Here, friction and the component of the weight are in opposite directions, so we find the difference. And that should give you 16 newtons, again, allowing for rounding to the correct number of significant figures. And then that should give an acceleration of 16 over 2, which is 8 meters per second squared. And notice this one is a deceleration of 9 meters per second squared. That's an acceleration of 8 meters per second squared. It decelerates up the slope at a greater rate than it accelerates down the slope. I'm stressing particular syllables in that last sentence to try and emphasise using the right terminology at the right time to describe the right thing is absolutely vital if you're going to be writing about physics.